Have you ever heard someone say, I just don't have the energy for that? Or maybe you've heard someone say, I need to save my energy. We use the word energy all the time in our daily lives. But do we really understand what it means? Well, simply put, energy is the ability to do work. It's what makes things happen and keeps them going. So for those of you studying right now, it's because you have the energy to do so. And those of you who are already falling asleep, they don't have the energy. You guys may want to go get some coffee. Now, everything around us, from the movement of a car to the warmth of the sun, is the result of energy. Without energy, things can't move, whether that's an object through space or a particle vibrating at one particular point. Now, energy can take many forms. When it takes the form of movement, it's called kinetic energy. In the form of warmth, it's called heat energy, and so on. An important point to note here is that energy can neither be created nor destroyed. It can only change forms as the object that it's acting on undergoes some form of physical change. For example, as a spacecraft enters back into the atmosphere, it meets air resistance, and it trades off its kinetic energy for heat energy. This is one of my favorite concepts in all of physics, and that's why we're definitely exploring this deeper. Now, in order to better understand what energy is and how it's connected to work done, let's look at an example of a person pushing a cart across a hall. Now, this person is putting in a certain amount of effort to do so. What would you say would increase the effort it takes to get the cart across? Well, there's two things. The first is the harder you have to push, the more effort you have to put in. And the second, the longer you have to push for, the more effort you have to put in. And those two factors are exactly what the concept of work done or energy consumed is based on. For example, if the cart is heavier or facing greater resistance, you'll have to put in more effort, which means more work needs to be done and more energy is needed to move that cart. Similarly, if the cart has to be pushed over a longer distance, more work needs to be done and therefore more energy is needed. In other words, work done is a product of the force applied and the distance that comes off of it. Now we can show this in the form of this equation, where F is the force applied to make an object move, and S is the displacement that object goes through as a result of that force. Now the reason it's so important to understand this is because energy is essentially the work done on an object to make it go through some kind of change. Now the energy that facilitates movement is called kinetic energy, which is the energy an object has due to its motion. Now kinetic energy is all around you, and you've seen it so many times. If you've seen a ball rolling down a hill, a bird flying in the sky, or a car that's moving on a road, you've seen kinetic energy. And we calculate this with the formula Ek equals to 1 over 2 mv square, where m is the mass of the object and v is its velocity. Don't worry, if this looks complex right now, we'll break it down for you. Now, as we've talked about earlier, energy is essentially the effort it takes to cause change. So for movement, this energy relates directly to how massive an object is and how fast it's moving. Meaning the more massive an object is, the more kinetic energy is needed to produce that movement. And similarly, the faster an object is moving, the more kinetic energy it has. And this is exactly what's captured in the kinetic energy formula. Now, as amazing as that would have been, this formula was not just written across the sky one random day, it was derived. And we'll do the same thing here. Using the equations of motion, we're going to derive the formula for kinetic energy. Let's imagine a car at rest, where a constant force F is applied from its engine, causing it to accelerate over a distance s. Now this means that there's work being done on the car, and that's why its kinetic energy is increasing. In other words, the mechanical energy from the engine is creating a force F, which is causing this energy to be converted into kinetic energy or movement. Now we're going to use this exact idea to derive the formula for the car's kinetic energy in terms of its speed, mass, and the distance it's traveled. Now, since we have no other interactions on the car, we know that the work being done by the engine is equal to the kinetic energy being generated. In other words, the change in kinetic energy is equal to the work being done. Now we also know Newton's second law, which says that force equals to mass times acceleration. And that's something we can plug into the original equation, and we'll get something like this. Kinetic energy equals to MAS. Now, we don't stop here. This is where we revert back to the original equations of motion, where we learned that the distance traveled, s, for an object accelerating from rest can be expressed as 1 over 2 at square, where a is acceleration and t is time. Now we can substitute these equations into our formula for work done and simplify to get 1 over 2 ma square t square. We just have one more step left. Now we know that v is equal to the acceleration multiplied by time, that is v equals to at. When we substitute this equation into our previous formula, we'll get the final equation for calculating kinetic energy, which equals to 1 over 2 mv square. Now this formula tells us a lot more than just how to calculate kinetic energy. It tells us that more mass means more kinetic energy. And similarly, more velocity also means more kinetic energy. And believe it or not, it also tells us that kinetic energy, measured in joules, is a scalar quantity. Now you may be wondering how. Well, even though velocity is a vector quantity, its square, or v square, has no direction, and therefore it becomes a scalar quantity. So if you have an object with a mass of 2 kgs moving at a velocity of 5 meters per second, what is its kinetic energy? Well, the formula for kinetic energy, again, is 1 over 2 mv square. And we can use that to calculate the kinetic energy of this object, which comes out to be 25 joules. Great! You're a pro at kinetic energy now. But let's talk about work though. Work done has some other interesting implications as well. It can show us how much energy is being converted from one form to another as the object moves. So if an object moves from a point of low potential to a point of high potential, it converts one form of energy into another. Let's take the example of you throwing a ball up in the air. What's happening here is you're basically using your arm to convert mechanical energy into kinetic energy. As the ball leaves your hand, it starts out with the kinetic energy that you've given it. We know two key things about this interaction. One, that the ball won't be traveling upwards forever. It'll eventually slow down and then come back towards the earth. And two, that energy can neither be created nor destroyed. It can only transform from one form to another. And that's why in this case, the kinetic energy is converted into something else. And that something else is called potential energy. So as the ball gains height, it converts kinetic energy into potential energy. Now, as the name suggests, potential energy is an object's potential to undergo change, and this can be based on its position or its state. In our case, the ball's height from the ground determines the amount of potential energy it has. And since this potential energy exists because of gravity, it's called gravitational potential energy. So basically what's happening is, as the ball is increasing its height, it's doing so against gravity, and therefore gaining gravitational potential energy. And since this energy is coming from its initial kinetic energy, the ball will stop moving upwards when it has converted all of its kinetic energy into gravitational potential energy. Try to stay with me here. This is exactly the same as doing work against gravity to move an object, that is the ball, into a position where it can then use that gravity to move on its own again. Now this one is a lot easier to derive. Now we know that work done is force into displacement. And in our case, the work done, or gravitational potential energy gained, is equal to the force acting on the object, on the ball that is, multiplied by the change in its height, that is displacement. I promise we're almost done with this one. Now let's break down the force here. Now we know this force is gravity, which is the mass of the object multiplied by the acceleration due to gravity. And there we have it. And that's how we get the formula for change in gravitational potential energy. And it looks like this. Change in gravitational potential energy equals to mg delta h, where m is the mass of the object, g is the acceleration due to gravity, and delta h is the change in the object's height. Let's quickly go over this motion one more time. As the ball is released from the hand, it has kinetic energy, which starts to convert into gravitational potential energy as it gains height and slows down. So we're losing kinetic energy and gaining gravitational potential energy. At the ball's maximum height, all of that kinetic energy will have been converted to gravitational potential energy. And this is the point where the ball will start to come back down, converting its gravitational energy back to kinetic energy. Now if we ignore air resistance, the energies will match up perfectly, which means that the kinetic energy at the beginning will be equal to the gravitational potential energy at the top, which will be equal to the kinetic energy at the bottom again. Now potential energy can take many forms. In the case of an elastic band, potential energy will exist because of the band's state. So, if the elastic band is stretched, mechanical energy is used and converted into elastic potential energy, which means that the stretched band contains the potential to create change, which is something we'll see when we release a piece of stretched elastic like a rubber band or a slingshot. In these cases, the elastic potential energy converts into kinetic energy. And we do have a way to calculate the elastic potential energy that's contained in a stretched elastic band. Because it's the same logic as before. The work that you do to stretch an object will be the potential energy stored in it, which means the force applied times the displacement that occurs while stretching the material. That is, elastic potential energy equals to F delta S. Now keep in mind that unlike gravity, the amount of force applied here isn't constant and changes as the object stretches. You need less force to stretch something in the beginning, but as you stretch it further and further, the force required increases. Now usually, this change in the required force is uniform, so we can just use the average force, which is why we're going to find the average of the force when there is no stretching, that is 0, and the force at the final point of stretch, which basically means we're simply taking half of the force at the final stretching point. That is, average force equals to 1 over 2 final force. Plugging this into the original equation, we get something like this. Elastic potential energy equals to 1 over 2 into final force multiplied by delta S. So if we have a slingshot and we put it back 1 meter using a force of 20 newtons, we can calculate the elastic potential energy by using the formula we just derived. That is, EP equals to 1 over 2 final force multiplied by delta S. When we've plugged in our values, our equation will be 1 over 2 into 20 into 1, which equals to 10. This gives us an elastic potential energy of 10 joules, meaning when we release this slingshot, it will transfer 10 joules of kinetic energy into whatever we sling in the slingshot. Now there are other types of potential energies as well. A prominent example is chemical potential energy. These aren't in the scope of this course, but we do encourage for you to research and find out about them in your spare time. The use of work, energy, and their conversion is extremely important in the world of science and engineering. It's something that's of crucial importance when it comes to designing things like engines, suspensions, and even tall buildings. And knowing how potential and kinetic energy convert and transform plays a key role in helping scientists and engineers in determining their designs.